Welcome back. In this video we're going to talk about Swan Assist. Swan Assist uses Swan, which was something we discussed in our previous video. Swan was a fully automatic approach to classify methods from a code base into different security relevant method types, as well as into security vulnerability types. And Swan Assist is using Swan to iteratively improve the results by adding new examples of the code base available into the training set of Swan. This is so-called active learning approach, and we are going to see how this works in the following. So this is a higher level overview of Swan and how this works together with the code base on one side, which is the input for our Swan, and then Swan uses this to label every single method from this code base into SRMs or vulnerability types. So this means the output of Swan was list of different methods, which are then can be directly used into the tools, or through so-called domain-specific languages. They can be used to specify the security rules for many of the SAST tools. So we are now introducing this part here, which is our tool Swan Assist. The idea is to introduce feedback from users into our training data, and users in this case are software developers or security experts who have knowledge about the code base itself, which is under analysis, and about security vulnerabilities in general. And the idea is that the user can adapt the learning by providing code-specific examples and labeling them, and this will come into the training data of Swan. Based on our experience when we were creating the classifiers for Swan, every time we have added examples of the code base we are analyzing, we have seen quite some improvement of the precision. And this is the very simple idea that this tool is enabling the users. So on the lower part here on this figure, we can see again the main components of Swan, and on the upper part we are introducing now the feedback from the user. The user can select arbitrary number of methods from the code base and label them. Once this is done, this is coming to the training data, which means Swan will create new classifiers based on the same features, but all with the new training data, and the user can run Swan then to get new improved SRM lists. Additionally, we have developed an algorithm, Swan Suggester, which will propose to the user what are the most impactful methods from the code base, in this case representing our test data, to be labeled and fed into the training data. So this is something we'll explain in short. First, Swan Assist is implemented as an Eclipse. Is implemented as an IntelliJ plugin. So users can simply install this plugin, and they will get an additional view on this, which can be on the site, for example, and this view will list all the methods from the training data uh, initially, and then when user will run Swan, so on this button here, user can run Swan once, then user will see the generated lists, and you see, so they are all have different kind of markings for sources types, sinks types, and so on. And it's a hierarchy tree because each SRM type will be then labeled further into CWE type. And user can give the feedback by updating these methods. Then using this wizard, user can rearrange the classes of this specific method. For example, here do get. Additionally, user can directly use the editor by clicking right on the method names, and maybe add completely new methods from the code base that he's working currently on, which they will land into the training data later. User can decide to run Swan at any time. There are some additional usability features. If you want to have a full tool demo, please check our tool video. Okay, so the question is, how should users choose this should choose these methods? One type of users are definitely security experts who, if they are familiar with the code base, they will definitely have the knowledge to select the right kinds of methods to be added. However, users like software developers, they are familiar with the code base, but they often do not know much about security vulnerabilities. So we, instead of just randomly selecting methods from code base and playing around, we have designed this algorithm which always proposes two methods to the users, and I'll shortly explain the idea. You have the pseudo code here on the right. It is important to know that for this algorithm we need the features. So all features in Swan, we have performed a one at a time analysis in order to find which features are most impactful for the learners or for the classifiers. And we have created a rank of features. So this function here, Swan features, will get us a ranked list of features based on their impact. And every time the user decides to run this algorithm, two methods will be selected based on the best ranked feature at the moment. Once this is covered, then next feature will be selected in the next iteration, and when all features are finished and there are still methods and the user wants still to label methods, then new rank list will be added from beginning. And the idea is that each iteration there will be chosen two methods from the code base that were never labeled before, and that are a good positive and negative example for the currently feature that is on top of the list. Based on this, we've seen that the classifiers have changed the most. So these two methods have the highest probability of the highest impact on the change on the classifier. So this is the idea that we are using in this algorithm, and yeah, in our evaluation we tried to see whether this actually works. And yeah, so what we wanted to answer with our evaluation is how much of manual training now Swan requires to get optimal classification. So we said a possibility is that user can always randomly select methods, and then there is another possibility to use our Swan suggester. And in this experiment, we measured how many methods on average we would need in order to get like perfect precision, like 100%. And for this we chose one real-world application, which was GXA. It's a genome expression atlas, and this was a relatively small application. We chose it smaller because we manually labeled all methods. As you see, there are 1663 methods, and then we labeled all into sources, sinks, and also CW89, which is SQL injection. Then we ran actually Swan iteratively until all methods from the testing data, which is the GXA application, come to the training data. So we start initially with our training data in Swan, and in each iteration we are adding 2 methods from the GXA application by labeling them correctly into the training data. In the first round we are using Swan suggester algorithm for doing this, and in our second round we were using always 2 randomly chosen methods from the application GXA. And we have done 10 runs of this in order to have a statistical significance. And yeah, this graph actually shows now on the x-axis you see the number of runs. So we have about 1600 methods. We had about 800 runs, because in each run we are adding 2 methods. So in first iteration we start with pure Swan default mode, and then every time we are adding 2 more methods. And on the y-axis you see the precision. So in this application initially Swan will classify, so this graph is actually, I think, for the sources. So if you want to see the other graphs, you can check our paper, but they have all similar trends. So the idea is that we started here under 78% of precision in the beginning. So that, as you see, when we have a random selection, that is the gray line, the improvement of precision is relatively slower and steady. And when the user would use a suggester algorithm, then you see that we have quite faster improvement of precision in the beginning. This means that for users who are using our Swan suggester, they would reach relatively high precision with less number of manually labeled methods. So based on this graph, we have that the precision reaches 0.8 after 31 iterations, or that is in total only 4% of the application methods in this in GXA. Yeah, so this actually shows that with comparing this algorithm, suggester will definitely be good improvement, and we can gain relatively good precision in by labeling manually a small portion of the application code methods. Okay, and in the next video we are going to see now how the inferred security relevant methods can be used in in combination with domain-specific languages to feed the taint analysis tools.